Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guests today are Olivier Ezratty and Rob Whitney, co-founders of QEI, the Quantum Energy Initiative. Olivier, Rob, and I talk about why the energy consumption of quantum computers is important, what drives this power consumption, how it changes with various technologies and algorithms, and much more. We hope you enjoyed this episode.
Hello, Olivier. Hello, Rob. Thanks for joining me today.
Hello.
Hi.
So, Rob, who are you and what do you do?
Okay, so thank you very much for inviting us. So I'm a quantum physicist. I worked on quantum physics since the late 90s, but in the last 3 or 4 years, I've been really more interested in the quantum technology aspects, in particular quantum computing. Before that, it was more fundamental questions of quantum physics. Now it's a bit more towards applications.
And Olivier, who are you and what do you do?
Well, I'm an author of a book, Understanding Quantum Technologies. I'm teaching, I'm training various companies, and I'm also doing a so-called techno screening. And as part of the work we're going to talk about, I'm kind of the engineer crossing the chasm between hardware, software, engineering, enabling technologies.
And I recently learned that both of you started an initiative called, I think, QEI. Would you mind telling me a little bit about that?
Yeah. So the Quantum Energy Initiative was created out of the idea that we need to look at the energetics of quantum technologies very early on. We need to understand it, how it works, how we can optimize it, and particularly with regards to quantum computing. We know that if we don't address that question, we may end up with having too power-consuming systems. And we know also that if we work on the optimizations of those systems, it could create very powerful and competitive computing systems with regard to the energetics. So it started actually last year with a PRX paper from our colleague Alexia Ofev called Quantum Technologies Need a Quantum Energy Initiative. And so we did it. So we launched formally an initiative it's about creating an international community of researchers and industry vendors looking at these issues, working together, sharing some methodologies, sharing also the science in an open way. And so at this point in time, we have a website, we have a community of about 300 participants. We have a board. We just created a scientific board. And we even have some industry vendor partners. So far, we have 24 partners, mostly from Europe, I would say, at this point in time, like IQM, Alice and Bob, Pascal, Paris TQC in Austria, Kilimanjaro in Spain, A-Quantum in Spain. And we want to expand that, of course. And one of the last news from I would say, the activity standpoint is we are launching our first workshop that will happen in November. In Singapore this year. And we already have a very interesting line of keynote speakers like Peter Zoller from Austria. We have Michel Devoret from Yale, Janet Anders from Exeter in the UK, and others, even from Japan. So that's where we are right now. Well,
So help me understand this. I think the conventional wisdom is that quantum computers take less energy than classical computers. And so one of the potential advantages for quantum, beyond, of course, the computational capabilities, is that you can do the same thing for much less energy. And if that's the case, why do we need QEI at all if we believe that quantum is going to take much less energy than classical?
Okay, that's a very good question. In some sense, that brings us to the research that we did in the CNRS to sort of answer this question, because on one hand, some people are saying exactly what you just said. On the other hand, some people are more or less saying the reverse. If you look at experiments that are done on a few qubits in the prototype quantum computers now, they're consuming sometimes even in the kilowatts per qubit, or a bit less, maybe a few tens or hundreds of watts per qubit. And so if you want to scale that up to millions of watts, you immediately start to see power consumptions of multiple nuclear reactors. So then the question was, how do we scale towards large number of qubits without exploding the energy bill? And that is sort of, I guess, brings us on to our research topic, which then led us to realize there's so much more to say on the domain that we need to create a broad interdisciplinary initiative. But so we just started with small elements, taking the expertise that we had around us here in Grenoble, in the CNRS and the CEA, and built a simple model of a complete quantum computer, from the end user to all of the electronics, cryogenics, everything you can think of. So the end user means they want to know the solution to a particular problem. So we took a problem that we believe, that most of us believe, is not soluble on a traditional computer, which was breaking RSA encryption, not because we necessarily think it's the most exciting problem to solve, but because it's one that's well documented. So we took that procedure of taking the best documented things for every element in the computer, and tried to build a model where you could actually answer this question, where you could optimize all the parameters and actually answer the question, well, how much power will it consume? And we're very happy that we managed to build the model. And then we put in various scenarios, and depending which scenario we took, we got all possible answers, from consuming a power consumption of multiple nuclear power stations on the worst cases, to consuming the same power as a few Tesla cars on the best cases. So now it's a question, so now that was just a first sort of scan of the domain. So now, but already it gives us indications and hints of things to avoid and things to go towards, to avoid going into the regime of multiple nuclear power stations. So I guess that's already the first sort of indication. And I should say we took a particular technology for our model of superconducting qubits, a little bit like, vaguely inspired by Google's computer Sycamore chip, but with rather futuristic view, so futuristic improvements. And even then, we sometimes still got into the regime of multiple nuclear power stations. So one has a lot of work to do at the level of the enabling technologies to control electronics and all of these things if you want to get down to more reasonable power consumptions. And that brings us to the interdisciplinary nature that we found that there were so many feedback loops between different scales in what we call the full stack. So from the how you choose to do the algorithm affects how you want to design the hardware, and how you design the hardware affects how you want to do the algorithm, and how you do the cryogenics affects how you want to do the electronics, in all of these sorts of things. So it really shows that you need an interdisciplinary group of, so which we are trying to construct by creating this community of people who can bring better information about the cryogenics from the cryogenic engineers, better information than we have about the electronics from the electronic engineers, better information about the algorithms from the quantum information experts, and bring that together and see if we can create a better, more realistic model for more different kinds of quantum computers, which gives us some better guidelines about how to compute without the cost being extravagant, let's say.
Let's break it down for a second. So you mentioned superconducting qubits. Mm-hmm. So out of the total energy budget of such a computer, what are the key parts? Is that the cryogenics? Do they take 95% of the energy, or is it something else? How does it break down for, say, superconductors?
So for superconductors, the big expenses seem to be, so every unit of heat that you generate at a cryogenic temperature, you have to spend a lot of electricity to extract. That's just the law of thermodynamics. So typically, for everything that's inside the cryogenics, so at cryogenic temperatures, it will be the cost of keeping things cool which dominates. But what we also realized is, so that's a big cost, and that was sort of what we were expecting. But the surprise was that we realized that the control electronics are a similar order of magnitude for the budget, even when they're sitting at room temperature. So the all of the electronics that generates all of the microwave pulses that are going to go to the qubits to control the qubits and to read out the qubits, is not negligible, which we weren't expecting. And depending how good if you could make your cryogenics quite good, quite efficient, then it could even start to dominate the budget.
What we start to see is that it's very different across different types of qubits.
Yeah. So that's
other types of qubits will have different energetic bills. Sometimes the lasers will consume a lot, typically for trapped ions or for cold atoms. In the case of photons, you're going to have mix of lasers, of controls, also from cryogenics, but less powerful because you don't cool it very low. You cool it at 4K. You cool the detectors and the photon generators. So it's a very different. It's very interesting to look at the energetics of all these various technologies, not just one.
And does that lead you to recommend one technology over the other? Say trapped ions is going to be much better than superconductors or something else?
So given that in the superconductors we have scenarios that vary from nuclear power stations to a few Tesla cars, I think it's definitely way too early to say that there's a technology that's going to win and another technology that's going to lose this.
But there are some insights still. The insights we have for trapped ions, for example, is we know that to scale trapped ions, you will need very early on to connect different QPUs, so different quantum processing unit. So then we will have to find a way to scale the interconnect technologies using photons usually, using conversions in some cases. And so we will have to look at the energetics of these interconnect solutions to have an idea on the way to respond to your question. So that requires to have a lot of people working together there as well.
Yeah.
If we pick on superconducting qubits, I don't think they want to take more energy on purpose, right? They say, well, we have to have cryogenics, we have to have control electronics, and so on and so on. So assuming they're not switching to a different modality, what can a superconducting vendor do to reduce the energy footprint?
Okay, so there are a bunch of parameters. So maybe just to mention a couple of them and not to try and be exhaustive is probably more interesting. So the first one that comes to my mind is the wires that come down from room temperature to the qubits conduct heat. And there's a limit to how much you can reduce the heat conduction of those cables. And so the smart thing to do is to say, how can I reduce the number of those cables? And that's all about multiplexing. So if I can put 10 qubits at the end of one wire and still address them individually, for example, by putting them at different frequencies or something like that, so I can talk to all of them individually, then that's 10 times better than if I have one qubit at the end of each wire. So those sorts of clever tricks about multiplexing and reducing the number of wires per qubit are clearly winning strategies, I think. But the price, there's always the thing, this is one of the things we realize is there's always a price to pay. So the price to pay is more crosstalk between qubits. So you send information to one qubit, but if there are too many qubits being addressed by the same wire, then it will tend to increase the noise that's felt by the other qubits. So you need to find the sweet point between the two. And that's where a sort of an optimization of the type we're thinking about enables you to make progress by finding the sweet point between energy consumption and quality of the qubits. Which brings me nicely to one other thing I wanted to mention, which is for us, we think it's very important, and it makes me think of the discussion you had about benchmarking in your podcast a couple of weeks ago, which was that we suspect the right way to pose the question is to say, what is the energy consumption for a given desired result for the end user? Because there's a lot of questions of a playoff between quality and energy consumption at every scale inside the quantum computer. And what really matters is, can the quantum computer solve the problem you want it to solve? And that's your sort of fixed constraint. And then you can optimize everything under that constraint, but you need it to work. There's no point having a quantum computer that consumes much less but doesn't do the job it was built for. That's sort of clear. So we take that approach. So we actually called this our metric noise resource approach. So the metric is what you want the computer to do as an end user, and what requirements that imposes on the quality of the qubits. The noise is then the modeling of what all of the effects that disturb the qubits from doing their job. And then the resources are the things you bring to stop that noise disturbing the qubits. And so it's this sort of three principal elements, which are sort of the philosophical basis of these more complicated models we're trying to build to model these systems.
What's interesting is you can add one fact that there's some economics involved there, because we know that if we want to scale efficiently the control electronics, for example, we will have to have a new economics, a volume market for quantum computers, because that's what will drive those vendors to scale down the size of the electronics, the power consumption, when you increase the number of qubits. So it's about kind of having a new Moore's law for the control electronics driving the scalability of those quantum computers. It's a mix of science, technology, and economics.
I wanted to ask you, Olivier, you mentioned earlier that there are several hardware vendors. I mean, you mentioned IQM and maybe others that are engaged in QAI. To what extent does a hardware vendor consider energy consumption as a first order problem? I mean, don't they first have to get the computers to work and do something useful before they address how much energy they consume?
Well, it happens that we hear that a lot from customers themselves. So we have customers who think that in the short to mid-term, one of the justifications to move to quantum computing, particularly in the NISQ regime, is going to be a lower power consumption, because HPC consumes a lot. So if you can replace existing classical HPCs and supercomputing with a more efficient, energetically speaking, quantum computers, it makes a lot of sense. But of course, to make that possible, all the hardware vendors have to create better quality qubits. We know that. I mean, whatever the technology, whatever the NISQ or FTQC approach, they need that. But once they will have done that, they will have to look at this as well. So it's kind of dual approach. And all the hardware vendors that we've been talking to, even the large ones from the US, they all are motivated to look at the energetics of the system, because we live in a world of finite resource where we can't escape that. And we as a community, I mean, the whole quantum computing community and even technologies community as a whole, we have to have a discourse on that. We can't say we sell new stuff, whatever the cost. We have to say what is it going to cost, including energetics.
But when I go to a store in the US and I want to buy a refrigerator, it says, well, the energy cost for this refrigerator is so and so many dollars per year. Do you anticipate that vendors will say, well, to run our computer, this is what the energy cost is going to be? Do you expect that there'll be standardization around that?
Yes. We want even to create some benchmarks around that. It will take some time, not ready. It's not ready yet, but we're already starting to work with the standardization and standards body worldwide, like I3D, to launch a discussion about creating benchmarks around the energetics of those systems. But it's going to be important to follow the approach that Robert described, the MNR approach, because it's not just the power consumption per se. It's the power consumption compared to what you want to achieve from a business standpoint or from the algorithm standpoint.
And I think maybe more generally, I mean, I agree that if the primary objective is to make a quantum computer, or more generally quantum technologies, because we're also interested in extending these ideas to quantum sensing or quantum communication and so on, but we're not experts in that. So that we need other people in the community to come and help us or take the ideas for themselves and go with. But if in quantum computing, if we want to make a quantum computer that works, that's clearly the first goal. But it might be a little bit too early to think about energetic or more general resource consumptions, but I think it's important to be too early than too late. And I think for many technologies in the past, maybe we were a bit too late to think about energy or resource consumption. So if people think we're a bit too early, I say good, right? And I maybe even agree with them, but I think it's worth already considering the issue at this stage.
Earlier, Rob, I think you mentioned the algorithm itself. How much does the power consumption of a system vary between it sitting idle and not doing anything except that all the electronics are on, as opposed to actually running an algorithm?
So that depends how much of the electronics you can turn off when it's not doing anything. So typically in the superconducting circuit that I know best, even if the electronics are switched on, you don't send microwave pulses to actually flip the qubits, to change the qubit state, to do gate operations, except when you're actually doing the gate operations. So immediately you have a big difference between the amount of power that you are sending down to the qubits from when the qubits are doing something, from when they're just waiting for the next step in the computation. And that is one of the critical elements which connects the hardware design to the algorithm, because a lot of the microwave signals, because you have to protect the qubits against noise, the qubits are typically also very well protected against the microwave signals you want to send. So you have to send very strong signals through all of the filters that protect them against the noise. And so most of the microwave you said is dissipated as heat, which you have to evacuate with your cryogenics. So at the moment when you're actually sending signals, there's a lot more heat to evacuate than when your qubits are just sitting waiting for the next instruction. So if you have an algorithm when most of the time, most of the qubits are waiting for the next instruction, it's quite a different optimization problem from when most of the time, most of the qubits are doing some sort of operation. And that's particularly noticeable in superconducting qubits. In other technologies, it may be very different. In some cases, you have to control the qubits all the time anyway, just to protect them against basic noise. So then the difference might not be so extreme, but it's one of the things we'd like to look at.
And what we know is the way the compilers are being designed with their optimization and transpiling features is going to play a key role. And at some point, we may have to embed energetics as a way to set up and parameterize those compilers. So software is going to play a very key role in the energetics of quantum computing, that's for sure.
How much collaboration do you need with the quantum computing vendors to create accurate models? And how much collaboration are you actually getting?
Well, at this point in time, we need more collaboration, probably more openness, more data on the full stack approach of all these systems. And your question is right on point. It's not easy. It's not easy. We want to build some kind of open science approach. That's why we organize our workshop in November. And we'll see how vendors get open. But hopefully there's also fundamental research being done in parallel with the vendors, which can bring a lot of stuff as well. Robert?
Yeah. So right now, in our first efforts, we took numbers we could find in the published scientific literature, which mostly comes from, well, some of it came from Google, but a lot of it also came from university and academic institutions. But of course, if we want to make better, more realistic models of what's really going on, or if we want to open our the codes that are developed by the community so that a vendor can use it to optimize their own setups, then that requires clearly some back and forth and and everyone learning from everyone else. And I think that's one of the exciting things about this subject is getting to talk to people with very different backgrounds and learning what there's going on, and learning also what other constraints there are apart from energetic constraints. Because of course, once you've built this sort of global modeling, you can put in other constraints. And probably that's worthwhile investigating.
As we get closer to the end of our conversation today, I wanted to ask you about the workshop in Singapore. So I assume that everyone in the workshop is going to come in and say, yes, energetics are important. We want to control and reduce the energy consumption of quantum computers. But what kind of presentations or tracks do you expect to hear in the workshop? What topics?
So, so we have, we hope to have a variety of people from a broad variety of subjects, scanning from very hardware-based things related to control electronics or cryogenics, to very theoretical things about what is even the meaning of energy in quantum systems. So we'd like to have a nice selection of people from all of those domains, and that everyone comes with a spirit of being willing to explain their little playground to people with a different background. And then the job of the people present, of all of us together, will be to try and develop a common language and perhaps a common set of questions, a common set of problems that we can then move forward with in small groups or in big groups. And so to try and create a dynamic of people who are open and interested in these subjects in general. I think that would be my objective for the workshop, and not set any particular constraints beyond that.
Olivier, did you want to add something to that?
Well, I can frame the workshop because we're going to have people from different fields, fundamental quantum devices, people working on quantum hardware, the actual qubits. We'll have people working on quantum algorithms and software, and it's very important to have all these people work together. And also we want to have people from the HPC world and hybrid computing world, because any quantum advantage, whether it's energetic or computational, has to be always compared to what we do today on actual classical systems. And so classical information processing is important for that to respect, and also because classical information processing is required to control all these qubits, particularly when you implement quantum error correction. So it's kind of interdisciplinary approach, and we want to implement that right away in our first workshop. But it's the first one, so we're going to learn with pride.
A supercomputer today, probably the energy consumption scales with the number of cores, right? If I've got 10,000 cores versus 20,000 cores, the 20,000 cores is probably going to be nearly twice as much. How is the scaling in terms of number of qubits? Is that exponential? Is that quadratic? Is that what does your model show there?
That's a good question. So I would say it's quite linear. So it's not so different. But what is perhaps very different from traditional computing is that in traditional computing, you often talk about flops or gigaflops and things like that. And those sorts of measures of a quality of a quantum computer have no meaning. So it's one thing to say it scales with the number of qubits, but how good are those qubits? What is their fidelity? What is their connectivity? What are all of those other questions? All of those other parameters which also affect the energy consumption. So if for example, every qubit talks to every other needs to have a connectivity with every other qubit, it could easily be that the scaling is much worse than linear, because you need the number of wires then needs to maybe scale like the square of the number of qubits or something, and so then the heat, just the heat conduction of the wires will scale like the square of the number of qubits. But so it really depends a lot on details beyond just a simple number right now. Maybe in the future we will get to a single sort of benchmark of quality, and then we can just say the number of watts for this quality, a bit like people do with the Green 500 in traditional supercomputers, where they give a number of gigaflops per watt, I think they give, or the other way around.
Yeah, it improved a lot recently. It went in a couple of years from 20 gigaflops a watt to 52 recently, with the Frontier supercomputing system installed at Oak Ridge, I think, in the DOE in the US.
So we're much too early to be able to give any sort of measure like that. but it's exactly the sort of questions we should be asking. What are the good measures? So what is a good measure of quality and what is a good measure of energy consumption? And then can you make a ratio which is a useful measure of efficiency? Or is it a multi-parameter space in which you can't do anything like that? I think those are very interesting questions, and I don't think we have really clear answers yet.
But that's good, because a good research program is about asking the right questions, not having the answers right away. So we ask a lot of questions to many people, and we ask them to work together to solve those problems.
My next to last question is a hypothetical question. So if you guys could have dinner with one of the quantum greats, dead or alive, who would that be? Olivier, maybe you first, and then Rob.
Who, dinner with whom, you said? I didn't get it.
One of the quantum greats, one of the famous quantum people.
Oh, the famous quantum people? We already have many connections, I would say. We don't miss those connections. What I would like to have is to have a group of the greats of this world, like the Jay Gambetas from IBM, Michel Devoret, Rob Sholkoff, and Alexander Blais from Sherbrooke, and also those guys working on electronics from Keysight, from Zurich Instruments, from SEEK, Oleg Bukhanov, Robert McDermott. I would like to have all these people in the room.
So more like a dinner party than a one-to-one.
Yes, exactly.
Yeah.
And I gave you the option of dead people as well, but
the dead ones. Oh, the dead ones.
Well, I for sure I would love to be a fly on the wall on the discussions that were happening in the 1920s that led up to quantum mechanics between Heisenberg and also the discussion between Heisenberg and Schrödinger, and who really to what extent they were inspired by each other, or they figured it all out individually, which I'm not an expert on the history of that, but I would be delighted to know that.
How can people learn more about the QEI and get involved?
Simple. We've got a website. So you Google Quantum Energy Initiative, you'll bump on our quantum-energy-initiative.org. We point to the QEI workshop. It's easy to find as well. We just checked that you can Google it, although the website is very recent. And you can find also the PRX paper from our friend Alexia Ofev that was published in June. We'll send you all the links, and we can make good use of it.
Very good. So Olivier, Rob, thank you so much for joining me today.
It was a pleasure. Thank you very much.
Thank you for inviting us. Bye-bye.